In this chapter, we will be continuing your study of trigonometry. In this lesson, we will be introducing you to angles written in standard position and the basic trig ratios.
All right, hi everybody. Well, we're going to start a chapter on trigonometry here. And I know you've done trigonometry before, but what I don't want you to do is I don't want you to think that because you know how to measure the height of a tree with its shadow, that you know all there is to know about trigonometry. The truth is there's a lot more to it. And this course has got two major focuses here. First of all, what we're going to do is we're going to transfer trigonometry, what you know about trigonometry, over to the coordinate plane, and that'll be the first part of this chapter that we're working on. The second half of this chapter is going to be to take some of the rules that you've got with trigonometry, and we're going to learn how to apply them to triangles that are no longer right angle triangles. And you'll see how kind of easy and convenient that is. But anyway, so here's how we begin here. So you've got trigonometry developing as a branch of science here, and you've got your right angle triangle. Okay, so here's your angle. Okay, we use the Greek letter theta to represent the angle typically. Right, there's your opposite side. Here's your adjacent side, and here's your hypotenuse. And these are always, the ideas of opposite and adjacent are always defined with respect to whatever angle it is that you're looking at on the right triangle, okay? So if this was the angle that we were interested in, then we would define the sides a little differently. This would be the opposite, this one here would be the adjacent. Now the hypotenuse is always going to be opposite the right angle. And in fact, in this particular course, it's important that you remember that. The hypotenuse is opposite the right angle. So if you're talking about a triangle that's not a right angle triangle, then there's no hypotenuse. Okay? Now, then come along René Descartes, and he's the one that introduces us to the coordinate plane, and mathematics really explodes with the introduction of the coordinate plane. You can visualize a lot of the relationships that up to that point had been very, well, a lot more kind of cerebral. You got to really think about what's going on there. This one became a lot more visual, easier to get your head wrapped around what's going on here. Now, trig guys want to be able to play over here on the coordinate plane, so the guys working on the coordinate plane say, oh, come on, bring your triangles here, let's have a good time. So we take the triangle and we slap it over here onto the coordinate plane. Now, we're going to analyze an angle, okay? Trigonometry really is, I mean, it's about the measures of the angles and sides of a triangle, yeah. But we typically, when we do trigonometry, we're focusing on an angle, okay? The sine, cosine, tan of a particular angle here. So it's about the angle here. Now, if you're going to draw an angle, if you're going to draw the vertex of an angle somewhere on the coordinate plane, where would you put it? Well, if you're like most people that I've asked this to, you'd probably put it right here on the origin. And that's exactly what we did, okay? So what we're going to do here is we're going to put the angle here on the origin. Now, the way most of these things work here, okay, standard position here, and this is what I'm defining here. We're going to create an angle, and we're going to call this standard position. We start with our initial arm, because remember, with an angle, you've always got two arms, right? Okay, you got it opens up here. You've got two arms of the angle here. So the initial arm is always going to be on the positive, okay, the positive x-axis. We're always going to start on the positive x-axis. Then what we're going to do is we're going to take our initial arm and we're going to rotate out like this. And this is going to be our terminal arm. That's where our angle is going to end. And so here's angle theta. Okay? So we got our initial arm here. We rotate out into the quadrant where we've got positive, where both x and y are positive. And just by the way, just as a matter of information, just to make sure you know, this is quadrant 1. Over here is quadrant 2. This is quadrant 3, and this is quadrant 4. Sometimes people make mistakes with that, but we counted out counterclockwise. Whoa, yeah, counterclockwise from the positive x-axis. 1, 2, 3, 4. Positive angle this way. Now, as soon as you do that, that introduces the possibility of having a negative angle, which is extremely exciting. Okay, you've got a positive angle, and now you've got negative angles here, because if we rotate clockwise, we're going in the opposite direction. Well, we got to have some way of indicating which way we're rotating. So positive angles go counterclockwise, negative angles go go clockwise. I keep getting that backwards. Counterclockwise, clockwise. Okay, that's really cool. Now, we're going to build a triangle because we're still talking about, okay, we're still talking about right angle triangles. We're still going to do trigonometry here. So here's what we do. Okay, we get our terminal arm drawn out there. Here's our angle theta. And then what we do is we take a point on that terminal arm, and to build that right angle triangle, we're going to drop it down here to the positive x-axis. Okay, we always drop it to the positive x, or sorry, to the x-axis. I shouldn't necessarily say positive x-axis because it depends on where you are. But we're always going to drop that line to the x-axis. Okay, so to the x-axis to build our right angle triangle. So that right angle will always be on the x-axis. It's really important that you remember that. Okay, if you ever draw that right angle to the y-axis, what you're going to end up doing is changing the definitions of sine, cos, and tan. Okay, now could we do it that way? Yeah, we could, but we don't. Okay, we don't define it that way. We always define it. Okay, when we stick to this pretty strictly. Okay, we always define it in terms of the definitions of the sides that we get when we drop the angle, or the side here, to the x-axis here. And we call that angle theta there, okay, theta is a rotation angle. And in this case, it's a rotation angle in standard position. All that we're going to be doing here is about analyzing that angle theta. Now you're going to see the introduction of other angles here, but that is the one that we're interested in. Okay, so little summary here, drawing an angle in standard position. Okay, the initial arm is on the positive x-axis, the vertex is on the origin. Going out this way is going to be positive, going this way again is going to be negative. Now the amazing thing about this though is that this opened up a possibility here, and this was cool for people that were studying trigonometry here, studying the way triangles work, is that if I start here and rotate out here, if my terminal arm ended in the first quadrant, okay, then I would create a triangle that I'm completely comfortable with. I mean, I've been doing trigonometry for years and years and years. Yeah, run a simple right angle triangle. But as soon as that angle crosses the y-axis, now all of a sudden this angle is too big to be in a right angle triangle. And so the question is going to be, well, how do we deal with that? We'll talk about that in just a second, but that introduces some interesting possibilities here, okay? And then look over here. Notice we can keep going. We can just keep wrapping all the way around here. So trigonometry, as soon as we moved over to the coordinate plane, this started to explode into something that was more than just able to deal with right angle triangles, which is really cool. Now bear in mind that the positive y-axis is going to represent 90 degrees. This would be 0 degrees here. If both your terminal arm, if your terminal arm was on the positive x-axis, that's 0 degrees. That's 90. Out here would be 180. Down here would be to 270. And when we come all the way back here, this angle right here becomes 360. Okay? So when that terminal arm wraps all the way around here and ends up pointing this way here, that could be a 0 degree angle, or wrapping all the way, that could be 360 degrees. Okay? So what we see happening here is this system here, the way this looks, wrap that all the way around. Well, 0 degrees and 360 look exactly the same. 1 degree and 361 degrees look exactly the same. 10 degrees, 370 degrees look exactly the same. Okay? Except for we might draw that little line to represent the angle, the rotation here. But in terms of when you drop the little triangle, because remember we're gonna drop a line here to the positive x-axis. Well, 10 degrees, okay, 10 degrees like that, and 370 degrees are going to look exactly the same. We're going to have the exact same triangles. So what happens here is the trigonometric properties of an angle depend on the terminal arm. Totally, entirely on the terminal arm, which is why 0 degrees and 360 degrees would be trigonometrically the same. 10 degrees and 370 degrees would trigonometrically be exactly the same. There'd be no different, okay? Because it all depends on where that terminal arm points here, which leads us to something that was like just amazing that they didn't know about trigonometry until they started to look at it in this context here. These functions here are what we call periodic. They repeat. Okay? Every 360 degrees, you're going to see a repetition here. Now, it depends on which trig functions you're looking at if it repeats 360 degrees, and that's something we'll talk about later, but you're getting this repetition now. Okay? So we really only need to study the angles up to 360 degrees, not even including 360 degrees if we start at 0. We only need to study those angles to get a sense of what everything is going to look like, no matter how many times you go around. Okay, so this is getting kind of exciting here. Now, we got another angle here to introduce, something to talk about here, and that is the reference angle. Okay? So here's what's going on here. And I'll try to maybe just fit this in right here. Maybe I'll zoom in. Whoops, wrong way. I'll zoom in here so that you can get a real good sense of what it is I'm talking about. So let's say you draw your triangle here. Here's your terminal arm. Here's your theta. And let's say that you went through the point here, just for argument's sake, let's say it's the point 3, 4. Now, what that means here is that this distance here is going to be 3, this distance here is going to be 4. Okay? So the tangent of that angle right there, the tangent of theta, okay, is going to be 4 over 3. Now, I could go a little bit farther than that, okay, because I could use the Pythagorean theorem and get that this is going to be 5. And I did that on purpose, 3, 4, 5. So I could tell you that the sine of that angle is going to be opposite over hypotenuse, 4 over 5, and the cosine of that angle here is going to be 3 over 5. Okay? Now, but here's where this gets to be really interesting here. I could take that triangle and flip it over the y-axis. So that now the triangle does something like this. Now, this is now my new theta. This is like, let's say, theta 1. This is now theta 2. Now I've got this new angle here. That's the rotation angle. That's the one that I'm studying, remember. This is going to be -3. This would be 4. And again, the hypotenuse here would be 5. It's the exact same triangle. Okay? It's the exact same triangle. So this theta 2, as soon as I cross the 90 degrees, remember I'm taking a point on that terminal arm and I drop it to the x-axis. Always do that. That right angle is always on the x-axis here. But it's the exact same triangle, so I'm anticipating that there should be some very, very clear connection between the trig functions here because I'm producing the exact same triangle. And actually, yes, we do. Okay? And what we end up doing here is we end up defining our trig functions in a slightly different way here. Okay? Because notice the way I've drawn this here. Okay? Now, granted, 4, for example, is not opposite theta 2. So there's an angle in here that I got to worry about here. The angle inside the triangle is what we call the reference angle. Okay? So, and this angle right here is going to be exactly the same as what that angle was right there. But we call it the reference angle because the way we're going to do this is we are going to define all of the trig functions for theta 2 to be identical to the trig functions that I would use to get this alpha right here, this reference angle. So to try to make this as clear as possible, the tangent of theta 2 is going to be the side opposite my alpha here over the adjacent here. So this would be 4 over -3, or if you want negative 4/3. I wanted to put -3/4 here, but -4/3. The sine of theta 2 is going to be the sine of that angle, which would be 4 over 5. Now, interesting, it's the exact same. That is the exact same as what we found for that first angle. Maybe I should put theta 1 here. Okay, that is an interesting little property there. Okay, the tangent changed because the adjacent side became negative when we flipped over to the second quadrant. But the y-coordinate didn't. It was positive in the first quadrant. It's positive over here. That's interesting. The cosine of theta 2 is going to be -3, the adjacent, over 5. Now, granted, my tangent, my cosine changed, but look how they changed. Tangent here was positive 4/3. Cosine here was positive 3/5. They're both negative when we move into the second quadrant because the x-coordinate is negative. Okay? Now, if I take that exact same triangle and drop it into the third quadrant, watch what happens. This is still -3, but now the y length here, the vertical length here, becomes -4. The hypotenuse stays 5. This is the angle that we're studying. This is my theta 3, if you will. And again, by definition, I'm going to say all of the trig functions for theta 3 will be identical to the trig functions that we get for alpha here, for my reference angle. And remember, that angle is going to be the exact same angle as we got right here in the first quadrant. Now in this case, okay, tangent of theta 3 is going to be -4 over -3. Well, the negatives will cancel. -4 over -3, I'm going to get +4/3. And that's kind of crazy because that takes us right back. That's the exact same trig function that we get right there. Okay, +4/3. That's amazing. The sine of theta 3 will be now -4/5. And the cosine of theta 3 is going to be -3/5. So this time sine and cosine were negative because of where we were located, but tangent became positive. Okay, and we got to go one more here. If we flip this now into the fourth quadrant, again, the exact same triangle. Okay, this is going to be now my theta 4. This will now be +3. This will still be -4, and the hypotenuse will be 5. +3 because now I'm pointing, the x value is now pointing in the positive direction here. Okay, in quadrant 4. There's my alpha. Okay, there's my reference angle. Again, just to keep saying this, it will be exactly the same as that angle that we had in that first triangle in quadrant 1. Okay, but now, we'll start with tangent again. The tangent of theta 4 is going to be -4 over 3. The sine of theta 4 is going to be -4 over 5. But this time the cosine of theta 4 is going to be +3 over 5. Okay? Again, because all of these ratios here for theta 4 will be identical to the trig functions for alpha, the reference angle, in that triangle right there. So the opposite side is the -4, the adjacent is the 3, the hypotenuse is the 5. Now there's a few things that we want to yank out of this, a few ideas here, okay? Again, the reason why we're linking these, okay, we are always studying the rotation angle, so the angle from here to here. But when you take that triangle and flip it over into the different quadrants here, because we're using the exact same triangle, we're assuming there's got to be some consistency between the trig functions that we're creating, okay? So we developed this idea of this reference angle because that angle in the triangle never changes. Okay, but we're allowing, because we're moving around the coordinate plane, we're allowing these negative signs to pop up depending on where we sit here. But one of the things you should notice, okay, is that tangent of theta is always y over x. Sine of theta is always y over the hypotenuse here. Now, we're going to use the letter r for hypotenuse. And I know that's going to seem kind of silly. Why would you use r for hypotenuse? But you're going to see why in a little bit here, okay? So let's just make a note of this. The r here is going to be the hypotenuse. And the cosine of theta is going to be x over the hypotenuse. Now, if you're wondering about the x and the y here, bear in mind that what we're doing here is we've got our terminal arm. We pick a point right here, and that's going to be the point x comma y. So we go x this way, we go y this way. We go x horizontally, we go y vertically. And then we're going to let r here be the hypotenuse, and so you know that r squared is going to be x squared plus y squared. Okay, so just by flipping that triangle around, we kind of force these ideas to pop out. Okay? Another thing that popped out, now we're really not going to talk about this in a lot of detail right now. This will come up a little bit later. But anyway, just there are things that are significant. Notice that in the first quadrant, when we did this up here, all three of the trig functions here had positive values. But in quadrant 2, only the sine did. Okay? And that's because tangent and cosine both are influenced by the value of x when you're in the second quadrant. In the third quadrant, the only one that was positive was tangent. Now that's because both x and y are negative here and those canceled. Okay? Over here in the fourth quadrant, only cosine was positive because these other two are affected by the y coordinate, and that's negative in the fourth quadrant. So we've got another little interesting rule here that we will call the cast rule later on. Okay? Whoops, sorry. The cast rule tells us where everything's positive. All of them are positive here. Sine is positive here. Tangent's positive here. And cosine's positive here. The cast rule, C-A-S-T. Now, I know that right now I'm probably going through this really, really too fast. A lot of information has come at you real quick, okay? I'm only doing this because it's all related, and later on in this chapter here, we're going to talk about a lot of these things again and again. I'm kind of giving it to you all right now, kind of laying it out on a platter so that you've got the whole thing, and then we're going to attack it kind of piece by piece, and we're going to develop these ideas a little bit further here. But they're all connected to this idea of this reference angle. Okay? Now, let's zoom out a little bit here. Whoops, wrong way. I've written all over the place here. But now, just to get an idea of how this works in the different quadrants here, in the first quadrant, if you're talking about an angle that's between 0 and 90, okay, then the reference angle and the rotation angle end up being exactly the same thing. If you're in quadrant 2, it's a different sort of thing here. Here's your reference angle. In quadrant 2, the reference angle plus, whoops, I don't know why I put 8 there. I meant to put theta. The reference angle plus the rotation angle, the relationship there is that when you add them up together, you get 180. Now down here, theta is bigger than 180. And the reference angle goes from 100 from the line, the negative x-axis, the 180 degree line, out to that terminal arm. So what happens here is in the third quadrant, if you took theta and subtracted alpha, the reference angle, in this case, there you would get your 180 degrees. Okay, theta, which goes beyond 180, subtract that reference angle, go backwards, you get 180. And then finally in your fourth quadrant, here's your rotation angle, and then this angle right here is your reference angle. Well, notice if you put those together, you go around the full circle. So here, theta plus alpha is equal to 360. Okay? Wow, that's just a lot of information. Okay, but like I said, we are going to now come back and start to grab little bits here and answer questions about those. Now you've seen everything, so I'm hoping that as we go through this, as we kind of refer back to these things, it'll ring a bell. You'll see the connections a little bit more clearly than you might otherwise. Okay, so let's take a look at some questions here. Draw each of the following in standard position. Okay, I'm asking you to draw them, then we're going to identify a couple things here. So 250 degrees. So now remember that this is 0, 90, 180, this would be 270, and then we come back around here and this would be 360. So 250 is going to be between 180 and 270. Now, I don't really care, like don't pull out a protractor here and measure this out and then line that up. I really just want to see a terminal arm that points into the third quadrant. It doesn't even have to be proportionally correct because that's not what we're trying to get at here. And when I ask you to draw the angle, I want you to be very specific. I want you to draw that little curve, go from the positive x-axis, rotate that around to the terminal arm, so that I know that you're talking about the positive angle, not the negative one here. If you just leave that, draw that out there, I'm not entirely sure what you're referring to. Now notice that this points us into quadrant 3. You don't have to use Roman numerals for the quadrants, but a lot of times you'll see people do that. And now the reference angle, let's think about that. The reference angle is the angle inside the triangle. If we draw that angle up to the x-axis here, or the triangle up to the x-axis there, that angle that I've got is larger than 180, but how much larger? What is this angle inside that triangle there? So if you take 250 and you subtract 180 from it, okay, you'll get the 70 degrees there. Okay, that's 250 degrees. We're going to subtract the 180 to see what's left. There's my reference angle. 320. Now I already knew that this was 0, 90, 180, 270, 360. So 320's got to be into the fourth quadrant here. And I'm going to draw this around to identify that it's the positive angle I'm referring to. Okay, it's clearly we're in quadrant 4. And now the reference angle. Now the reference angle is going to be the angle inside the triangle when I draw it. So I draw the triangle up to the x-axis. It's going to be this angle right here. Now remember, in the fourth quadrant, that rotation angle, if you add that to the reference angle, that should be 360. So to get the reference angle, it'll be 360 minus the rotation angle. And the difference there is going to be 40 degrees. So my reference angle here would be 40 degrees. Now in this question right here, we're just specifically asking you to identify the reference angle. It's a really important skill, and it's something that you're going to have to be good at even when you move on to the next level of trigonometry beyond this course. So the angle here, the rotation angle that we're given here, if you can't see that there, and you probably can't, the number that they're giving us here is 330. We're obviously in the fourth quadrant, and so I want to know what the angle is to finish the triangle here, okay, in the fourth quadrant. Well, if that's 330, remember that together they have to add up to be 360. So 360 degrees minus 330 degrees, the difference between them is going to be 30 degrees. So the reference angle here is 30 degrees. Okay. Over here, now our rotation angle is in the second quadrant. When I create the triangle, I go down to the x-axis, so the angle that I need is right here. Now bear in mind that out to the negative x-axis, that would be 180 degrees. 150 stops right there. So the difference between them, 180 minus 150, so I take the 180, subtract the 150, should give me what that angle is left over there. And that's going to be, again, 30 degrees. Okay, 30 degrees. Now, interesting thing here, in both of these cases here, the reference angle was 30 degrees. That means that we're using the exact same triangle to create the angle here for 150 degrees as we are to create this 330 degrees. That means that there should be a connection between the trig ratios here. If the triangle is the same, the trig ratios are the same, but we're in different quadrants. So I want you to think about that. So what would be the difference here if we're putting the triangle in different quadrants? Same triangle, just different quadrants here. And if you haven't kind of figured that out yet, the difference is going to be the signs. Whether something's positive or negative will depend on what quadrant it's in. But if you're using the exact same triangle, then the numeric value of those ratios is going to be exactly the same. Now, another thing you're probably going to notice after a while here is that we don't often ask you, I mean we will, but we won't often ask you for the reference angle if you're in the first quadrant. That's because that's the boring one. The reference angle and the rotation angle are exactly the same thing in the first quadrant. Okay, that's kind of trig as it was earlier when you were learning trig. Same old, same old. Okay. Okay, so now in this case here, we're giving you some information here. We want you to figure out what the reference angle is and then what the measure of the rotation angle is. Now, and this figuring out the measure of the rotation angle, and we probably should throw in the word rotation in there. We don't really need to. That's usually the implication. If I just say the angle, we're referring to the rotation angle. But anyway, this is important when we start to solve trigonometric equations. You're going to see that this is actually what we're going to do here. When we do the solving, the first thing you're going to find typically will be the reference angle, and then you got to use your knowledge of the way the diagrams work to get that rotation angle. So here we go. So in this particular diagram right here, we are looking for this. There's our rotation angle, and then we're told that the terminal arm has gone 60 degrees beyond 180 degrees. So now when you draw the triangle there, okay, when you draw the triangle, that angle right there has got to be 60 degrees. That's our reference angle. But now, that's 60 degrees beyond 180. So the rotation angle here has got to be 180 degrees plus 60 degrees. And the answer is the rotation angle, the actual angle that we're trying to study here, is 240. Okay. This next one. Same thing, here's our terminal arm. So what we're going to do to start off with is we're going to draw that right angle triangle. And notice that the angle here, okay, the angle between the terminal arm and the x-axis, that's the 50 degrees. And again, that is our reference angle. That's the angle inside the triangle. We're in the fourth quadrant. So the relationship between the rotation angle and that triangle here, when we put those together, we should complete the full circle here, which means that rotation angle that we're looking for is going to be 360 degrees less, we went all the way around to the x-axis, but when we drop backwards 50 degrees. So the answer here is going to be 310 degrees. Okay, that's the angle that we're trying to study here. And this last one, and this one is meant to be a little bit of a trick here. Notice that the angle that we're giving you here is 40 degrees. Now, but if you draw the triangle, you draw the triangle down to the x-axis. We never ever go to the y-axis, okay? So if that angle there is 40, then I got to think about that. This is supposed to be 90. From the positive x-axis to the positive y-axis is 90 degrees. If that's 40, that means this angle here must be 50. And that angle inside the triangle, as we saw before, that angle is the reference angle. And as I said a few minutes ago, the reason why we don't typically ask about this is because the relationship is kind of boring. Okay, if the reference angle is 50 degrees in quadrant 1, well then the rotation angle is 50 degrees in quadrant 1. They're the exact same thing. Okay, this question we're going to do something similar, just without the benefit of the diagram here. We're going to try to do this a little bit more abstractly here. So we've got a reference angle of 10 degrees in quadrant 4. Now I want you to think about what that looks like. Okay, if you can, before you answer this question here, that would be ideal here. But so if you can think about what the answer is without drawing it out, that would be great. 10 degrees in quadrant 4. Now in quadrant 4, the reference angle and the angle should add up to 360, which means this one here should be 350. But if you're not seeing that, little quick sketch here makes a big difference. What that means is we're looking for this angle right here, and we know that this angle here is 10 degrees. Together, again, you can see they add up to 360, which means this one has to be 350. Okay, angle of 200 degrees. Now let's think about that. The way they break up here, remember, is 0, 90, 180, and then 270. So 200 degrees puts us clearly in quadrant 3. Now, 180 degrees is the boundary between quadrants 2 and 3. So think about the question is, how far beyond 180 did we go? And the answer is 20 degrees. Okay, and you can see that again by just drawing this out here. 200 degrees puts you out here. Again, this is 180, and I'm a little bit beyond that. Okay, quadrant 2, 67 degrees. Okay, now 67 degrees. Now think about that. What that means is if we're in quadrant 2, we've rotated into quadrant 2, but we're going back 67 degrees. Okay, now and again, if you're not sure what that's referring to, you can draw that out here, but that should be 180 minus 67, so 113 degrees. And again, that's the quadrant 2 tells me to do that. Okay, quadrant 4, okay, this angle is going to be 360 minus the reference angle. Quadrant 3, okay, it's the angle here is going to be 180 plus the reference angle. In quadrant 2, it's going to be 180 minus the reference angle. With 100 degrees, we're actually back to quadrant 2 because we're beyond the 90 degrees, but not quite at 180. Now just think about that. 100 degrees. 100 degrees. Now, to get to the x-axis would be 180. So what am I missing here? How much more do I need to go here? Well, I need to go 80 degrees. Okay. So it's really important that you're able to kind of put all of this information together, that you can see the link between the angles, okay, and then what quadrants that we're in, and how the quadrant, for example, how the quadrant and the reference angle give us this guy right here, the rotation angle. But then you should be able to take the rotation angle, I should say, and split it up into its reference angle and what quadrant you're in. Okay, now one of the things that I want you to notice by this is that in a lot of cases here, when we do these reference angles here, we're usually going to have the case that alpha here is acute. Okay, it doesn't necessarily have to be. When we talk about reference angles, okay, what we're talking about here are angles whose trig, actually probably the word that we should probably use here are related angles, okay? Related angles. These are angles that have the same trig ratios. Now the signs might be different, but if you drop the signs, if you ignore whether it's positive or negative, you're getting the exact same numeric value. Those are related angles. When we use the word reference angle, we're typically referring to a situation where that angle is acute. We're using the smallest positive value we can as a related angle. Usually that's going to be acute, or let's say 90 degrees. Okay, maybe we wouldn't go beyond that. So we might use an acute angle or a 90-degree angle to make that work. Okay. Anyway, but it's for our purposes here, it's almost always going to be more convenient to go to an angle that would be like in the first quadrant as we develop these ideas in this course. All right. So now here we're going to talk very, very quickly about reflections on the x-axis or the y-axis or both here. And so here's again an idea that I started a little while ago. Now we're coming back to it to discuss what's going on here. What we're going to use is we're going to use the x-axis, or the axes I should say, as mirrors, and we're going to reflect that triangle, okay, over the axes here, with the idea being that that angle inside the triangle, that's the one we're going to call the reference angle. And again, because it's inside that triangle, that's why the reference angle that we're using is typically going to be acute, like we mentioned a few minutes ago. Typically, okay? You certainly wouldn't consider an obtuse angle to be a reference angle. It might be a related angle, but not a reference angle, because that's not the way our trig definitions usually work. Typically, if you think back to Math 10, SOHCAHTOA, those are with respect to acute angles there, okay? So what we're going to do here is let's determine the angle in standard position when 36 degrees is reflected. Now let's reflect this to start off with in the y-axis. So if you take 36 degrees, reflect it in the y-axis, then it's going to open up like that. So the question is now, what's this angle? Well, if it was 36 degrees there, this is going to be 36 degrees right there. So if you reflect that in the y-axis, that's going to be 180 degrees minus 36 degrees. Whoops, okay? So 180 degrees minus 36, okay, is going to be 144, whoops, equals 144 degrees. Now if you take that and reflect that in the x-axis, okay, that 36 degrees is going to open up down here. It's kind of like on my negative 36, if you will. But anyway, it's going to be 36 degrees in there. I'm in the fourth quadrant, but the angle that I'm really looking for is this guy right there. So it's going to be 360 degrees less that 36 degrees. Okay, so 360 degrees minus 36 degrees will give you 324 degrees. And if we reflect them in both the x and the y axes, okay, so let's say I reflected it here, reflect it back down, it's going to be down here. This will be my 36 degrees. Even if I reflected it in the x-axis first and then the y-axis, it's still going to put that angle right there. And again, the angle that I'm interested in this case is the angle that goes all the way down to here. So 180 degrees plus an additional 360. Okay, so 180 degrees, whoops, plus 36 degrees, and that's going to get us 216 degrees. Whoops, that's the angle that we're looking for. Just using the idea of reflecting, and we're talking about it in those terms just to give it kind of a visual link, something that you can see. When we go from quadrant to quadrant, it would be better that you didn't think of it necessarily in terms of the algebra and try to remember the rules. Like, it would be better if you didn't think, oh, okay, in the first quadrant, theta is alpha, in the second quadrant, 180 degrees minus alpha is equal to theta. Down here, 180 degrees plus alpha is going to equal theta. I don't know why I'm writing it like that. Making a mess. Equals theta. And then over here, 360 degrees minus alpha is equal to theta. You can memorize these little rules here, but if you can visualize us kind of reflecting these angles around the coordinate plane, that's probably going to be a whole lot easier to remember the relationships.
In this next section, we're going to introduce you to the basic trigonometric ratios, but we're going to limit ourselves to angles that are in standard position in quadrant 1.
All right, so now we're going to go and now, I guess, officially talk about the basic trig ratios, okay, in quadrant 1, and then we're going to go expand this around the full circle here. So let's say you've got your terminal arm for angle theta, your rotation angle goes through here, and we pick a point, any point on it, x comma y, and we drop that altitude to create the triangle here, so we go over x, go over y. There's my right angle, and we know, we've already talked about this, we can use the Pythagorean theorem to get r, and r will be the square root of x squared plus y squared. We already know that. Now, the way this is defined, and the fact that r can kind of be pointing in any direction here, just as a convention here, we're going to define r to be greater than 0 at all times here. This isn't going to be the plus or minus square root of that. Okay, it's just going to be the positive square root. Now, I'll tell you right now, the reason why we're using r is because if you held r constant, okay, if we held r constant, just the distance that we're going to go from here out to here, and we checked in on all the different triangles that you can create. So we let theta get larger and larger and larger. If what you can do, you can probably see this here. What you would, oh, that's terrible. What you would end up doing here is drawing, okay, you're going to draw a circle. You're going to draw a circle. Just take my word on it. Oh, that's embarrassing. That was terrible. Okay, you're going to get a circle, and so r would be the radius of the circle. That's why we use r for the hypotenuse, because it's the radius of the related circle here, okay? Blah. Anyway, but this does give us an opportunity now, as we did earlier, to identify the different trig functions now based on this new, these new values here, okay, or these new variables here. So think about your primary trig ratios, okay? Given your triangle here, here is your theta. The way this is defined here, the opposite side is the side that basically subtends the arms of the angle that we're creating. The adjacent side is one of the sides used to create the angle. And then it's the side that's not the hypotenuse. The hypotenuse is usually the easiest one to identify because it's the one opposite the right angle. It's the largest one in a right angle triangle. And so now you know that your sine ratio, or sorry, the trig ratios here, the sine of that theta is going to be the ratio of the opposite side to the hypotenuse. The cosine will be the length of the adjacent divided by the length of the hypotenuse. And tangent will be the opposite over the adjacent. And so we get this little SOHCAHTOA. Okay? Okay, opposite hypotenuse, cosine is adjacent hypotenuse, tangent is opposite adjacent. Okay, that's just a way of remembering the different ratios there, okay? But now we're on the coordinate plane. So things are going to be a little bit different. I want you to start to relate the opposite side to the y value of that point. I want you to start to relate the adjacent side to the x coordinate of that point. Okay, and then the hypotenuse will be r here. And so in this case right here, we're going to get these new definitions. Okay, sine is now going to be the y coordinate divided by the radius. Cosine will be the x coordinate over the radius, and tangent will be the y coordinate over the x coordinate. So now what you get is, instead of SOHCAHTOA, you get this. Ticks. Anyway, it's still SOHCAHTOA, okay? It's just that opposite is now going to be replaced with y, and there's like a deeper meaning there, okay? We're talking about the y coordinate of a point on the terminal arm. Adjacent is going to be replaced with x. X is going to be, okay, the coordinate of that point on the terminal arm. And so we should be able to, build the trig ratios now for any kind of angle based on these definitions. And in fact, we're going to stick really, really doggedly to these definitions. These are going to apply regardless of what the rotation angle is. And now hopefully this is going to start to kind of clue in here. The reason why we're making this change here is so that we can go past 90 degrees. If all we do is we limit ourselves to the opposite adjacent hypotenuse, we are stuck with angles in a right angle triangle that have to be acute. The rotation angle has to be acute here. But if you make this transition, okay, this idea works whether you're in the quadrant 1, quadrant 2, okay, x, y, r, quadrant 3, quadrant 4. It doesn't really matter here. X, Y, R. We can make those definitions work for any theta that we're interested in studying. Okay, so the question we're being asked here is we're being told the point 15,8 lies on the terminal arm of theta, and we're going to find the exact value of the three primary trig ratios, and we're going to find theta to the nearest degree. Okay, so now we got to figure out where that is. 15,8. Let's draw that. 15,8. They're both positive, so that's going to be somewhere out here. There's my terminal arm. Here's the point 15, 8. Now that tells me something here. If I draw the right angle there, this is going to be 15. That's going to be 8. Now, the one thing I don't know when I'm given the point here is I don't know right off the bat what the r is. But I know that r is going to be the square root of 15 squared plus 8 squared. And if you spend a couple seconds on your calculator, you'll discover that that means r is 17. Worked out really quite nicely here. Now, so here's my theta. That means the sine of my theta, if I think about my new definition, is going to be the y-coordinate divided by r. That's 8 over 17. The cosine, okay, and remember, I want you to relate sine to y, cos with x. The x-coordinate there of that point was 15, and I know that the r-coordinate was 17. Or the r value, I shouldn't say coordinate, I should say r value. And then finally, tangent, okay, which was opposite over adjacent, it's now going to be y over x is going to be 8 over 15. So now I've got the three different trig ratios for that particular theta that goes through that point right there. Now, if I want to figure out what that angle theta is, I've got three different trig functions that I could use here. Now remember, the unknown is the theta. So what I've got to do to get theta, okay, when I take the sine of theta, it's producing 8 over 17. So that's the sine of theta gets me 8 over 17. I got to get rid of that sine there. I've got to get rid of that sine there. And the way I do that is I take the opposite. I do the opposite of sine to that theta there. And if I do the opposite of that to the left-hand side, I've got to do the opposite on the right-hand side. So this will be the sine, the inverse sine of 8 over 17. Now, when I go to my calculator, a couple things. I got to make sure, first of all, I got to hit mode here. I got to make sure I am in degree mode. Okay, let's zoom in on that. I got to make sure that the degree is highlighted there. By default, the calculator goes to radians, and you'll talk about radians later, but right now we want to be in degree mode. And then second sine to get the inverse sine operation. And in this case, I wanted to do 8 divided by 17. And normally we're going to round angles to the nearest degree. That's just kind of the convention here that we will normally take here. So 28 degrees. Now, just to verify that that is in fact the truth here, and it shouldn't matter which one we use, I'll do that with cosine as well. Okay, so second cosine, in this case it'll be 15 divided by 17, and actually I'm a little concerned that I hit another button there, and I did. Divided by 17. Whoops, sorry for the reflection there. Press enter, boom, 28. And in fact, if I do this with tangent as well, oops, what did I do? Oh, sorry, second tangent, and 8 divided by 15. This should also get me the exact same angle, and it does. In all cases here, we're getting approximately 28 degrees. So it doesn't matter which one of those things I choose, I'm going to get 28 degrees as my answer. All right, this question right here is essentially the same as the one that we just did. Okay, with one little difference here. Okay, so 3, 6. Okay, we draw that out here. 3, 6. Okay, drop it right there. Here's the point. 3, 6, which means horizontally the x value here is going to be 3. Vertically, we're going to get 6 here. So r will then be, because I need r, is going to be the square root of 3 squared plus 6 squared. Okay, well, 3 squared plus 6 squared. Now that is going to be the square root of 9 plus 36. So it's going to be 45. Okay, now here is where this differs slightly from the last question, because in the last question we could take the square root and we got an answer that was beautiful, 17. Square root of 45 isn't going to work like that. And the expectation is at this point that you will simplify that. Now think about that. 45 is going to be 3 times 3 times 5 if you break that into its prime factors. And I think it's always easier to utilize this tool. I know there are other methods, there are shortcut methods for doing this, but it really depends on you, how your comfort level with perfect squares, perfect cubes, and all that stuff here. But I think everybody here, with a little bit of determination, can always break down a number into its prime factors. There's a pair of 3's in there, and what a square root does is it takes pairs of factors inside and spits out a single. So then the square root of 45 will reduce down to 3 root 5. A single 3 comes up. There's nothing I can do with the 5 there. It stays there. So now I can write this out. The sine of theta here, whatever that theta turns out to be, this is going to be the y coordinate, 6 over r, which we know is 3 root 5. Now, I can simplify this a little bit. These are both multiplied together in the denominator. There's the 6 divided by the 3. I can do that. 6 divided by 3 is 2. But I'm stuck with a root 5 in the denominator. Okay? Now, depending on the order in which this course is kind of coming at you here, you might be expected to go a little bit further here. That might be as far as you're expected to take it, by the way. 2 divided by root 5. But again, depending on the order that you do this in, you might be forced to do something what we call rationalizing it. What we mean by rationalizing is we don't particularly like having a square root. Okay, the square root of a number other than a perfect square down in the denominator. It's just a weird thing there. That's going to be an irrational number. But I can get rid of it by multiplying numerator and denominator by the square root of 5. Basically, by squaring that number down there, I can change it from this irrational number to an integer. Root 5 times root 5 will be 5. But then I'm stuck with a 2 root 5 in the numerator. Okay? Now, this may be an accepted answer. That may be an acceptable answer. It depends. That's the best I can say. It depends. Okay? Depends who your teacher is and what your teacher is expecting. Cosine of theta is going to be 3 over 3 root 5. And again, 3 divided by that 3, the coefficient. I can divide the coefficients, but I can't divide out anything with the radical here because it's a radical. It's a different kind of number altogether. So 3 divided by 3 is 1. Again, that might be as far as you need to go. But you may be expected to square that denominator, and then that's going to get you a root 5 in the numerator and a 5 in the denominator. And then finally, the tangent of theta is going to be the y-coordinate divided by the x-coordinate, and that reduces down beautifully to just 2. Now, we are in the second quadrant. Wow, I can't believe I said that. We are in the first quadrant. It shouldn't really matter which of these I use, sine, cos, or tan. And we've already seen an example of that. What I'm going to do, though, is I'm going to use the inverse sine. I'm going to do it on these two separately here, just to show you that these are both going to give me the same angle here. So theta is going to be the inverse sine of, let's say, 2 divided by root 5. I'll go to my calculator here. So second sine of 2 divided by the square root of 5. And to the nearest degree, I'm going to get 63 degrees. Now, just to illustrate that what I did here was okay, if I put 2 root 5 over 5 into that, okay, let's take the inverse sine of this. The inverse sine of 2 root 5. Now I got to make sure that when I do this, I either close the brackets around the radicand here or I move out, okay, so that it's just the square root of the 5 there, divided by 5, close the brackets, and there it is again, 63.4, or just 63 degrees. So they are exactly the same ratio there. Again, it depends on your teacher what form you're going to be expected to take that to. Okay, in this question right here, we're asking you to do something that's essentially related to what we've just been doing, but we're asking you to come at it from a different direction. I'm telling you that sine of the angle theta is 2 over 3 in quadrant 1. So instead of asking you to give me the sine ratio, I am giving you the sine ratio. So now we're still in quadrant 1, so we're going to drop that triangle right there. But I want you to think about what I've just given you here. I have told you the sine of theta is 2 over 3. Now think back to the definition. Sine is going to be opposite over hypotenuse, but we're changing gears a little bit. Opposite, that's going to be the y-coordinate, so 2's got to be the y-coordinate, and 3 has got to be the r, the hypotenuse. So this is going to be 2 and 3. Now the question is asking me to come up with the other two trig ratios, the cosine and tangent there. Well, what I need is x. So based on the information that I've got here, I know, okay, that r is supposed to be the square root of x squared plus y squared. So that's going to be 3 is equal to the square root of x squared plus 2 squared. So now to get to the x here, I'm going to square both sides. So that's going to be 9 will equal x squared plus 4. Bring the 4 over. 9 minus 4 is going to be 5. And so now, whoops, x could be, oh, that eraser's not working the way I want it to. X could be the positive or negative square root of 5. When you take the square root like that, I don't know if you meant the positive or the negative one here. But in this particular case here, because I'm talking about an answer or a line segment that's going to be in the first quadrant, that's got to be the positive one. That's got to be positive root 5. Okay? So now my other two trig ratios here, the cosine of theta will be the x value, root 5, divided by r, which is 3. Now in this particular case, I'm okay with that. I'm okay with having that root 5 in the numerator. It doesn't matter if I've got a rational, an irrational value in the numerator. It's only the denominator that I have an issue with it. So that's fine. Tangent of theta is going to be the y-coordinate over the x-coordinate. So that's going to be 2 over root 5. And again, that might be okay. That might be okay. It might not, though. So it might be that I have to multiply numerator and denominator by root 5 to get 2 root 5 over 5. Now, the last thing that they wanted us to do was to come up with the angle. Okay, and I'm going to, because I was given the sine of theta was 2/3, we're going to use that one. So I'm going to do the inverse sine of 2 divided by 3. And I will round that to the nearest degree, so 42 degrees. So theta will equal the inverse sine of 2 divided by 3. And I got 42 degrees. Okay, and this last question that we're going to do is very, very similar to the one that we just did. So the ratio for tangent is 3 over root 7 is going to be in quadrant 1. We want to find the other two trig ratios again, and then we want to find the theta here. So again, we're in the first quadrant. We drop our altitude there to create the triangle. But remember, this time I told you that tangent was 3 over root 7. And by definition, our new definition here, this is our y and this is our x. So I've actually given you those two coordinates right there. So y is going to be 3, x is going to be root 7. Now I got to get r, and that's going to be the square root of x squared. So in this case, root 7 squared plus the y-coordinate squared there, which is going to be 3, so 3 squared. So that's going to be the square root of 7 plus 9. The square root of 16, oh, that's beautiful, works out to be 4. So the radius here is going to be 4. Now, not plus or minus, just positive. Just positive, because there's, just by definition, there's no negative orientation to that. Okay, good. Good. So now, sine of theta will be 3 over 4. Okay, y over r. Cosine of theta will be root 7 over 4. X over r. Now, if I want to figure out what the angle is, theta, I'm probably going to go back, just in case I made a mistake somewhere up here, I still want to get the correct answer. So I'm going to use the inverse tangent of 3 over root 7. Go to my calculator. So second tangent, 3 divided by the square root of 7. Okay, and rounded to the nearest whole, I'm going to get 49 degrees. Good. I hope that's starting to give you a sense of how these things are all related here. One of the things you're going to find with trigonometry, particularly now, and as this moves on into your, even after this course, the next course that you take here, there is no single idea that we're going to deal with here that's going to be really complicated. Where you're going to run into problems is just the multitude of these little things that you got to keep straight. There's a lot of little details here to keep your head wrapped around. But there's no one big idea here that's really overwhelmingly difficult.